What's up, math scholars and math haters? This is Mr. W. Today we are going to start talking briefly about an idea called proportions. And you can see a whole bunch of numbers in fractions and a whole bunch of weird pie-looking things here on this board. I will explain what each of these are, but first I want to talk about the basic idea of a proportion. The basic idea of a proportion is that we have two fractions that are equal to each other. That's it. That's the only thing. And I actually drew a quick representation of 1/2 and 3/6. For 1/2, I drew a circle with half of it filled in. For 3/6, I drew a circle with 6 pieces. 3 of those were filled in, but I think we can see, even despite my bad drawing, that I have filled in the same amount of each of these circles, even though I've used different numbers to represent them. This goes back to the idea of an equivalent expression. And when we see an example like this, where we know 3 of the numbers in a proportion and we're trying to find the 4th, it's a little bit like an equation. And there's a more equations-based way we can solve this, but I wanted to stick to the easier way for right now, which is just finding a multiplying or dividing pattern. So essentially, over here, if I didn't know one of these numbers, I could go ahead and use the fact that to get from the left fraction to the right fraction, I could multiply by 3. 1 times 3 equals 3. 2 times 3 equals 6. That's another way that we can generate equivalent fractions. Another pattern I could have used, however, was an up to down pattern, where I said, okay, from 1 to 2, we're multiplying by 2. From 3 to 6, we're also multiplying by 2. So that's the whole idea here, just finding these patterns. Finding patterns that will let us get from, for instance, the left side to the right side, or the bottom part to the top part, in order to figure out the value of a mystery number here. So let's go ahead and do that here. And if I want to go ahead and look, I can see that from left to right, I'm multiplying by 2. And if 5 times 2 equals 10, then what would 2 times 2 get me? Well, 2 times 2 would get me 4. And to go ahead and demonstrate this using these fractions, or using these circle charts that would represent the fractions, here's 1/5, here's 2/5, and now here's 1, 2, 3, 4/10. And even despite my bad drawing, I think you can see that I've filled in the same amount of circle. And again, that's the whole idea, the whole basic idea of what a proportion is. So next, I'll come down to these two examples here, and let me just go ahead and show you all 4 of these at once. All right, so here, I can see that I don't know this number, so I'm going to look for a multiplying or dividing pattern that goes either from the bottom row to the top row, or from the left fraction to the right fraction, in order to figure out the value of this number. And I believe the best way for me to go about this is to see that to go from the bottom row, the denominators, to the top row, I'm multiplying by 3. 5 times 3 equals 15, so then what would 12 times 3 give me? Well, 12 times 3, if you know your times tables, would be just 36. For this example, it's going to be the same idea, except it's going to be a little different, because now I'm going to have to divide. I can see that to get from my denominators to my numerators this time, I'm dividing by 3 instead of multiplying. So if 12 divided by 3 equals 4, what would 9 divided by 3 get me? 9 divided by 3 would just get me 3. So I can see that 3/9 is an equivalent fraction to 4/12, and these two fractions together make a proportion, just like 1/2 and 3/6, 2/5 and 4/10, and then 15/5 and 36/12. Either way, it's the same idea, and the goal is always the same, to get two fractions that are equivalent, that mean the same thing but use different numbers. So now let's come down here. For this one, I'm going to have to find either a left to right pattern or a top to bottom, numerator to denominator pattern. I think my easiest way to go here is going to be to see that I'm multiplying by 4 to get from the left fraction to the right fraction. 5 times 4 is 20. 3 times 4 is 12. Then finally, for this one over here, I do not know my bottom left number, which means that I'm going to have to figure out some pattern to get from the right fraction to the left fraction, or to get from numerators to denominators. The pattern that I'm going to use this time is going to be to see that 16 to 8 I would have to divide by 2. So now 14 divided by 2 would give me what? Well, if you look at your times tables, or if you know this in your head or whatever, you should get an answer of 7. So 8/7 is an equivalent expression to 16/14. So now the second idea related to proportions is called proportionality, and specifically we're looking at a table of x and y values. I'm going to just go ahead and show all of this at once. The basic idea is that in order to know that x and y are proportional, we just need to check and make sure that to get from x to y, we're multiplying by the same thing every time. So for this first example, 2 times what equals 10? 2 times 5. 3 times what equals 15? That's times 5 again. And 4 times what equals 20? That is also times 5. Now for the second example, this one is tricky. I intentionally made it very tricky. But let's go ahead and try to figure out if we're multiplying by the same thing to get from x to y. 1 times what equals 5? Times 5. 4 times what equals 8? Okay, this is a little weird. This is times 2. And now 2 times what equals 6? Well, that's times 3. And 3 times what equals 7? Who knows? Doesn't go in evenly according to our times tables. And y'all can very easily figure that out. If you do notice a pattern, though, you'll see that we're not multiplying by the same thing every time, we're adding. So we're actually adding 4 to get from 1 to 5, 4 to 8, 2 to 6, and 3 to 7. This is not what we're looking for. And if you see a proportionality question, chances are they might be trying to trick you by throwing something like this in, where they add the same thing every time and try to make you think that's what it is. But in reality, we're looking to make sure that we're multiplying by the same thing every time, which in this problem, we are not. Now down here, you might be able to tell that to get from x to y, we're actually dividing by 2. And dividing will work. You can go ahead and find something that you're dividing every time to get from x to y, and you can still say it's proportional, but this goes back to the idea of the constant of proportionality. And that's just the number we multiply x by every time to get y. So in this problem, instead of dividing by 2, if we want to think of this as multiplying, that's the same thing as multiplying by 1/2, or 0.5. So dividing by 2 is an okay way to represent this. But specifically in this idea of proportionality, we're looking for what we're multiplying. So if you're dividing by 2, you're multiplying by 1/2. If you're dividing by 3, you're multiplying by 1/3. If you're dividing by 4, you're multiplying by 1/4, and so on. And the last thing I'll do is just go ahead and write the constant of proportionality for each of these. For this one, the constant of proportionality was 5. 5 was the number we were multiplying. This one, no. This one wasn't proportional at all. And then for this one, that constant of proportionality was 0.5 or 1/2, however you would want to write that. I just wrote it as 0.5 here for the sake of space. But those are the two first basic ideas of proportions, just regular proportions, and then thinking about proportionality in a table of x and y values. If you're one of my students, good luck on your assignment. If not, good luck on whatever math work you have to do for this.